Okay, last week we had MAT 334 tests. So let's look at the questions and how we solve them against our exam. Question 1. We are saying given a system of linear equations in the form ax equal to b. So we have this. We have our equations to be of the form x minus y plus z equal to 1 minus 3x plus 2y minus 3z equal to minus 6, 2x minus 5y plus 4z equal to 5. So first things first, we are supposed to convert this to the form ax equal to b. So we'll be having this guy to be in matrix form. So in matrix form, it becomes 1 minus 1 1 minus 3 2 minus 3 2 minus 5 4 times x y z, and then it will be equal to 1 minus 6 5. So if we multiply 1 times x, 1x minus y plus z, we have the first equation. So we are asked to decompose the matrix A into lower upper triangular matrices. So we are asked to decompose this matrix A into a lower matrix and a upper triangular matrix. So basically A equal to LU. All right. Now we know from our LU decomposition method that our matrix A can be equal to LU, where L is a lower triangular matrix and U is an upper triangular matrix. And then our L and U are of the form 1 0 0, L21 1 0, L31, L32 1. Now our U is of the form U11, U12, U13, 0, U22, U23, 00, U33. Now we are aware that our L can as well be L11, L22, L33, but in that case, our U will carry 1 1 1. So basically, one of L and U must have its leading diagonal to be of element 1. So it's either I give my element 1 to L or I give it to U, but it can't be both of them. It will be either of them. So in this case, I want to make it L. Fine. Remember, we said that our A has to be equal to LU. So if I'm saying A equal to LU, then I am saying that our A, which is 1 minus 1 1 minus 3 2 minus 3 2 minus 5 4 should be equal to 1 0 0, L21 1 0, L31, L32 1 times U11, U12, U13, 0, U22, U23, 00, U33. So if we multiply these two matrices, we will have U11 as the first here, because 1 times U11 is U11, 0 times 0 0, 0 times 0 0. So move on to this guy, and the second column would have you have U12, and then the last one will have U13 here also. For the next row, we have this to be L21 U11. So L21 U11, if I multiply this to L21 U11 plus 0, I have this. Then the next one, L21 U12. L21 U12 plus U22, 1 times U22. All right, so for the last one, I'll have L21 U13 plus U23. And then for the last row, I will have L31 U11. We'll have L31 U12 plus L32 U22. Then I'll have for the last one L31 U13 plus L32 U23 plus U33. Of course, since we said that our A is equal to LU, then this matrix here should be equal to this matrix. So if we are going by element to element, we can say that our U11 is equal to 1, U12 is equal to -1, and U13 is equal to 1. So all of this are the same thing as all of this. So going to the next line, L21 U11 is equal to -3. But already U11 is 1. What does that mean? It means our L21 should be equal to -3. Fine. The next line, L21 U12 plus U22 should be equal to 2. Our row 2 column 2. That's 2. Already we've said that our U12 is -1 and L21 is -3. So that will give me 3. So it means that our U22 should be equal to -1. Should be -1. Again, U12 is -1. L21 is -3. That will give me 3. 2 minus 3 is -1. So our U22 is -1. For the last one, L21 U13 plus U23 is equal to -3. Again, our L21 is -3. U13 is 1. That's -3 here. That'll give me 0. So our U23 is 0. U23 is equal to 0. Fine. So we are done with the first 6 elements. Remains the last 3. So we go again. L31 U11 is equal to 2, which means that already U11 is 1. So our L31 has to be equal to 2. So let me circle our answers. So this is L21, this is U22, this is U23, and then I have my U11 to U13. So this is my L31 here also. So the next one, L31 U12 plus L32 U22 is equal to -5. So once again, our U12 is -1, L31 is 2, this is -2. If I take it here, it becomes +2, that's -3. But then U22 is -1, so my L32 has to be 3. So L32 is equal to 3. Let's go over it again. U12 is -1. L31 is 2. So this gives me -2. If I take it here, it becomes +2. So I have here -3. My U22 is -1. So I have this to be minus L32 equal to -3. So L32 has to be 3. Let me circle that one also. And then for the last one, L31 U13 plus L32 U23 plus U33 is equal to 4. So if we analyze again, our L31 is 2, U13 is 1, so this is 2. If I take it here, it becomes -2. That's 2 here, that's 2 there. L32 is 3, U23 is 0. I have 0 there, so it means that my U33 is 2. So our U33 is equal to 2. Fine. So the fact so that now I have gotten the values of L21 down to U33. So I'll go and write the values inside L and U, and that will mean that I have decomposed the matrix. So finally, our L becomes 1 0 0. L21 is -3. So I have -3, 1 0. L31 is 2. L32 is 3. Then 1. So this is our L, and then U will be U11. U11 is 1. U12 -1. U13 1. So I have 0. U22 is -1. U23 is 0. So 0 0. U33 is 2. So I have decomposed the matrix A into a L and a U. That's all. Now how do we confirm our answers? If you multiply these two, we should be getting our matrix A back. So let's see. The first row of L, the first column of U, I have 1, so I have my 1. First row of L, second row of U, I have -1, fine. Same for the last one, I have 1. So I have -3 here, fine. Here I have 3 -1, that's 2, fine. So it means that we are accurate. So we have decomposed the matrix A to a L and a U. That answers question 1A. So we are asked to find the variables of the said matrix, the matrix X, or the equations X minus Y plus Z equal 1, minus 3X plus 2Y minus 3Z equal to -6, 2X minus 5Y plus 4Z equal to 5. So we have to find the values of X, Y, and Z using the matrix inversion method. So of course, we should be considering, after we've converted this guy to AX equal to B, then our X can then be A inverse times B. So converting into matrix form, we have 1 minus 1, 1, minus 3, 2, minus 3, 2 minus 5, 4, times X, Y, Z equal to 1 minus 6, 5. So of course, this is our matrix A, this is the matrix X, and this is the matrix B. So the goal here is to get A inverse. Of course, to get A inverse, we need our determinant first, because we know that our A inverse is equal to 1 over determinant of A times the adjoint of A. So let's get determinant of A first. The determinant of A should be equal to 1 minus 1, 1, minus 3, 2 minus 3, 2 minus 5, 4, which should be equal to 1 times, so this is 8 minus 15. So 8 minus 15 plus minus plus. So that's plus 1 times. So here I have minus 12 plus 6. Minus 12 plus 6. Then I have my plus 1 into, so this is 15 minus 4. 15 minus 4. So we get this to be minus 7 minus 6 plus 11, which is equal to minus 2. So our determinant is minus 2. So of course, we remember from our basic algebra that to get the adjoint, so to get the adjoint of a matrix, we need to get the minor first. Of course, to get the minor of a matrix, we get the minor of the individual elements in the matrix. So the minor of A will be equal to the matrix. So for the minor of 1, we get the determinant of 2 minus 3 minus 5, 4. For the minor of -1, it will be minus 3 minus 3, 2, 4. So I have minus 3 minus 3, 2, 4. The minor of 1, I'll have minus 3, 2. So I have minus 3, 2, 2 minus 5. Then we go on to second row. The minor of minus 3 here, it will be minus 1, 1, minus 5, 4. Minus 1, 1, minus 5, 4. The minor of 2 will be 1, 1, 2, 4. Then the minor of minus 3 will be 1 minus 1, 2 minus 5. 1 minus 1, 2 minus 5. The minor of 2 is minus 1, 1, 2 minus 3. The minor of minus 5 is 1, 1 minus 3 minus 3. 1, 1 minus 3 minus 3. Okay, so the minor of 4 then will be 1 minus 1 minus 3, 2. 1 minus 1 minus 3, 2. So if that is clear, so the minor of A can then be, this is 8 minus 15, that's minus 7. This is minus 12 plus 6, that's minus 6. that's minus 6. This is 15 minus 4, that's 11. Minus 4 plus 5, I have 1. I have 1. 4 minus 2, I have 2. Minus 5 plus 2, minus 5 plus 2, I have minus 3. 3 minus 2, I have 1. Minus 3 plus 3, I have 0. 2. 2 minus 3, I have minus 1. So this is the minor of the matrix. And of course, from here we can as well get, after minor, we'll go and get the cofactor. So the cofactor of A is equal to the minor of A transpose. The minor of A transpose, and that one is easily minus 7 1 1 minus 6 2 0. No, the cofactor of A, the cofactor of A, the cofactor of A is minus 1 to power I plus j of the individual elements in the minor of A. So let's write as the minor of A like this. But note, it is basically saying that since this one here is A11, so our I and j are both 1, so that is even power. This one will be odd, even, and so on. So I have this to be, so basically, as I was saying, it should be plus, minus, plus, minus, plus, minus, and so on. So plus, minus, plus, minus, plus, minus, then plus, minus, plus. So we've gotten our cofactor. So then our adjoint can then be the transpose of the cofactor. So our adjoint can then be the transpose of the cofactor. Don't forget, our matrix B is 1 minus 6 5. So that we would hold that one. Of course, our determinant of A is minus 2. So cleaning this part, we can now get our adjoint. So the adjoint of A is equal to the cofactor of A transpose, and that is minus 7 minus 1 1 6 2 0 11 3 minus 1. So we've gotten our adjoint. Therefore A inverse is equal to 1 over minus 2 times minus 7 minus 1 1 6 2 0 11 3 minus 1. Now I can get my variables in peace. So our x is equal to A inverse times B, which is minus 1 over 2 times minus 7 minus 1 1 6 2 0 11 3 minus 1 times, so our B is 1 minus 6 5. So we get this result to be minus 1 over 2 into, so I have here minus 7 plus 6, that's minus 1, plus 5, that's 4. So this is 4. I have 6 minus 12, that's minus 6, plus 0. So 6, and so that's minus 6. Then the last one, 11 minus 18, that is minus 7 minus 5. 11 minus 18, that's minus 7, that's minus 12, so minus 12, which means that I have this to be minus 2 3 6. So the value of x is minus 2, the value of y is 3, and then the value of z is 6. So we've gotten our values. Our x is equal to minus 2, y equal to 3, and z is equal to 6, using the matrix inversion method. And then how are you sure you are correct? You can run these variables through your given equations. You know, we're told that x minus y plus z is equal to 1. So our x is minus 2, minus 3, that's minus 5, plus 6, that's 1. So if you run it through others two, you should get the answer. So this answers question 1b. Question 2 says we should construct a least square quadratic approximation for this function over the interval 0 to 1. Of course, whenever we have a question like this, it is continuous. So to do that, since we are dealing with a quadratic approximation, we should be saying that the approximation p of x should be a naught plus a1x plus a2x squared. So this is quadratic. Okay. So of course we want to get the residue of this function. So our residue is given as s equal to integral 0 to 1 a naught plus a1x plus a2x squared minus square root of x all squared dx. So basically we are considering either you consider integral a to b y minus p of x all squared dx, or you consider integral a to b p of x minus y all squared dx. In the long run, we'll be getting the same result. So for this case, I'm considering this second one. All right. So of course, I want to minimize our residue. That is, I want to get the s, the a naught, the s, the a1, and the s, the a2. And then of course, to minimize the residue, all of them have to give me 0. They have to give me 0. So the s, the a naught, a1, a2 must give me 0. So if I'll start with a naught, in this case, our the s, the a naught is given as 2 integral 0 to 1 a naught plus a1x plus a2x squared minus square root of x dx. Then we are saying that it should be 0. It should be 0. The s, the a1 is given as 2, or if we do that, we'll get 2 integral 0 to 1 x a naught plus a1x plus a2x squared minus root x dx, and then that one should give us 0. And then the s, the a2 will be 2 integral 0 to 1 x squared a naught plus a1x plus a2x squared minus square root of x dx, and that too should give us 0. So we are considering these three equations giving us 0. So if we'll be doing that, we will simplify these three equations, and from there we'll be solving for a naught, a1, a2, everything else, because every other thing there will be a constant. This one now will be a constant. Here I'll be having my variable to be a2. Here I'll be having to be a1, a naught. Same thing for the other equations. So let us expand together. For equation 1, or for these three things, I'll be having integral from 0 to 1 a naught dx plus integral 0 to 1 a1x dx plus integral 0 to 1 a2 x squared dx equal to integral 0 to 1 square root of x dx. So I'm saying that if I expand all of this, I'll be having a minus integral 0 to 1 root x dx. So taking it to the right hand side, it becomes plus. So I have this. For the second equation, I'll be having integral 0 to 1 a naught x dx. Why x? I'm multiplying all through by x. So I'll be having x a naught a1 x squared a2 x cubed. So the next thing here should be integral 0 to 1 a1 x squared dx plus integral 0 to 1 a2 x cubed dx, and then that will be equal to integral 0 to 1 x root x dx. And of course the last line would be integral 0 to 1 a naught x squared dx plus integral 0 to 1 a1 x cubed dx plus integral 0 to 1 a2 x to the power 4 dx, and that will be equal to integral 0 to 1 x squared root x dx. So everything we are seeing here, we can integrate from a naught to a1 up to the last one, integral x squared root x. We can integrate. So integrating all of that would give. So integrating all of this, we'll have for this first one. Well, of course, here I'll be having. I can make out my a because it's a constant. So I'm left with integral dx, which is x. So I'll be having 1 there. So this is just a naught. So it implies that I have a naught for the first equation. The second one, I'll be having x squared over 2. That's 1 over 2. So I have this to be 1 over 2 a1. Then the second one, the third one will be plus 1 over 3 a2, and that will be equal to, this is x to the power half. So it should be x to the power 3 over 2 over 2 over 3 over 2, which is 2 over 3. So I have this to be equal to 2 over 3. Of course, you can integrate all these things when you are reading. Next line, I have this to be 1 over 2 a naught plus 1 over 3 a1 plus 1 over 4 a2 equal to 2 over 5. The last line, 1 over 3 a naught plus 1 over 4 a1 plus 1 over 5 a2 equal to 2 over 7. Okay, so we have our equations, and then we want to solve simultaneously. So we are solving for a naught, a1, a2. So using any of the methods we were taught, so we can use the Gaussian elimination method, you can use the Gauss-Jordan, you can use the LU, you can use the matrix inversion. So whichever method you want to use, you use. But if you solve using any method, so solving simultaneously, we get, so I'll be solving mine with a calculator. You can solve yours using whatever method you are taught. Okay, bear with me. So we get our a naught to be in fraction 48 over 35, and in decimal it is, sorry, our a naught is 6 over 35. 6 over 35. Then in decimal we have it to be 0.1714 to 4 decimal places. A1 is 48 over 35. In decimal we have it to be 1.3714, and then A2 is minus 4 over 7. In decimal it is minus 0.5714 for 4 decimal places. So the polynomial that approximates this function is p of x equal to 6 over 35 plus 48 over 35 x minus 4 over 7 x squared, or 0.1714 plus 1.3714 x minus 0.5714 x squared in decimal. So this is a polynomial that approximates y equal to root x over the interval 0, 1, using the quadratic of polynomial, All right, so we are also asked to compare this our result with the exact solution of the function in a table. That is, we take values of x from 0 to 1. So of course you can take 0 and 1. You can take maybe 0, 0.1 up to 1. Anyhow you choose to go about it, you pick your values. All right, so if we are doing that, I can say that my x values, so taking this way, my x values, I want to take a spacing of 0.2. So I'll be using x to be 0, 0.2, 0.4, 0.6, 0.8, 1.0. So the next line will be for y of x, that is using the function itself, root x. So what would our results be? Starting with 0, when x is 0, of course I am dealing with root x. So when x is 0, I have my answer will be 0. My answer will be 0. So when x is 0, my y of x is 0. When x is 0.2, my answer is 0.4472 to 4 decimal places. When it is 0.4, I have 0.6325. For 0.6, 0.7746. 0.8, 0.8944, and when it is 1, we have 1. The next column will be for the polynomial that we got, that is our approximated result, that is this guy here. We'll be putting all these values of x and see what our polynomial will give. So if I write it on my calculator here, 0.1714 plus 1.3714 minus 0.5714 x squared. So when I solve when x is 0, I get 0.1714. 0.1714. When x is 0.2, we get 0.4228 to 4 decimal places. When x is 0.4, we get 0.6285. When x is 0.8, we get 0.6 instead. 0.6. We get 0.7885. When x is 0.8, we get 0.9028. And then when x is 1, we get 0.9714. Of course, we should be doing our error analysis too. So of course, our error is giving us is the absolute value of the difference between these two results. That is our y minus p, we get the absolute value. So our error here will be, so let's say is absolute value of y minus p. So whichever way you choose to subtract, no problem. I have this to be 0.1714. The next one will be 0.4472 minus 0.4228. That is 0.0244. 0.6325 minus 0.6285. That's 0.004. The next one, 0.7746 minus 0.7885. This is 0.0139. 0.8944 minus 0.9028. This is 0.0084. Then I have this to be 1 minus 0.9714, which is 0.0286. So by doing this, I have compared my I've compared the least square approximation with the exact solution. No, this is the least square approximation. and then this is the exact solution, and I've gotten the error using the quadratic approximation. So that answers that part. Then the last one is saying that we should give a sketch of the graph showing the quadratic approximation and the exact solution. So basically what we are told to do is draw a graph where our graph is to contain your x-axis and your y-axis. So if we are drawing our Cartesian graph like this, where this is your x and this is your y, of course they are all positive. So if I'm taking my x using these coordinates 0, 0.2, 0.4, 0.6, 0.8, 1.0, and then I say my y should go from, of course it's going from 0 to 1 also. So let's say it is taking 0.2 also, 0.4, 0.6, 0.8, 1.0. For y of x, when x is 0, y is 0, so I have it to be at this point. When x is 0.2, y is 0.447, so it's slightly above 0.4. So let's say it is here. When x is 0.4, y is 0.63, slightly above 0.6. So let's say here. For my sketch, my points are approximated and are now accurate. When x is 0.6, y is 0.7746. So that one should be between 6 and 8. So let's say here 0.8 to 0.8994, 98944. So that will be slightly above 0.8. And when x is 1, y is 1. So for root x, this is the graph. So this is the graph. This is the graph for root x. So this is y equal to root x. Now we are also asked to show for the second one. So we'll connect the dots for x and p of x now. When x is 0, y is 0.1714. So it should be somewhere around here, above 0.1. When x is 0.2, y by p is 0.4228. So 0.2, 0.422. That one should be below my y. So let's say at this point, of course, it is not accurate. 0.4 to 0.6285. That one should be below this, but it is lower than it. So 0.6285. 0.6, it is 0.78. It is above my y. So that one should be somewhere around here. Somewhere around here. Then 0.8, it is 0.9028. That one should be above. That one should be above. So let's say someplace here, 0.9. Then when x is 1, my y is 0.97. So that one should be below my 1 here. So if I'll connect the dots, I'll connect from here. So it goes like this. So this one now will be the line for what? For p of x. For p of x. So we have answered all the question for number 2. For number 2. Alright, for question 3, we're asked to use the Newton-Cotes formula to derive the Simpson 1-3 rule. Question 3. Want to derive the Simpson 1-3 rule. Okay, so we will be using the Newton forward formula that says y of x equal to y naught plus x minus x naught over h forward y naught plus x minus x naught x minus x1 over h square 2 factorial forward square y naught, and so on and so on. Now let's quickly picture something. We are dealing with numerical integration. We want to integrate a function over an interval. So let's say I have this diagram. All right, so I have this to be my function, and I want to differentiate over an interval a to this b. So I'm integrating this function over a comma b. Now the Simpson 1-3 rule is saying that we should break this interval into 2 into 2 subintervals. So we are breaking it into 2 subintervals. So this is our B. I'm breaking it into 2 intervals. So 1, 2. So I have 3 points basically. 1, 2, 3. Let me call this. Let me call it. Of course, this point here is the midpoint, so I can say it is A plus B over 2. A plus B over 2. So this is what we are doing. We want to integrate our function over an interval going from A to B, taking one step at the midpoint. Alright, so if we'll be doing this, we will be integrating our Newton forward formula from A to B. Now, I want to say that because our Newton forward formula is considering our values of x to be evenly spaced. So the difference between A and A plus B and B should be the same. That is, the difference in values of B and A should be 2h. So if I suppose A to be 0, then B will be 2h. And of course, A plus B over 2 will be h. So if I'm saying that my A is the starting point, which is x naught, so A is x naught, which is 0. This midpoint will be x1, which is h. So x1 will be h. And then x2, which is B, will be 2h. So we want to integrate our Newton forward formula over this interval. So let's do that. The integral from 0 to 2h of y of x dx will be equal to the integral from 0 to 2h of everything you are seeing here. Y naught plus x minus x naught over h forward y naught plus x minus x naught x minus x1 over h square 2 factorial for square y naught and so on dx. Of course, we already said that our x naught is 0, x1 is h. So let's write what they are here. Now I want to truncate my Newton forward formula at this third term, at this term, so that at that point there, the next thing here we'll be considering forward cube y, where I'll be having the particular x3 or y3. Now I don't want x3 because I don't know what x3 is here. So I want to solve it at the point where I have x2. So it means that I'll be truncating my formula at this point. So doing that, I'll have our integral 0 to 2h of y of x dx to be integral 0 to 2h y naught plus, remember, your x naught is 0 from here. So I have this to be x over h forward y naught plus I have x into x minus h over h square times 2 factorial for square y naught. I am truncating at this point. So it means that every other thing that we there would be dealt with in our error analysis. So if we would integrate this, I have our result to be xy naught plus x square over 2h forward square y naught plus 1 over 2h square into x cube over 3 minus x square h over 2 forward square y naught. And I have everything going from 0 to 2h. So putting the bounds, we get our x is 2. Of course, at the point where I put 0, everything will be 0. So I'll be considering only 2h. I have this to be 2h y naught plus 2h square over 2h forward y naught. This is forward y naught. Then plus 1 over 2h square into, I have 2h cube over 3 minus, this will be 2h square times h over 2 forward square y naught. Forget this one is something else. So at this point here we can simplify so that we have, don't forget, starting with integral from 0 to 2h y of x dx. So I can say this is integral from a to b, because we already said that our 0 is a and then 2h is b. So that works fine. So all of this then becomes 2h y naught plus, this will be 2h forward y naught plus 1 over 2h square into, this is 8h cube. So I have 8h cube over 3. This is 4h square. That's 2h square. That's 2h cube. So minus 2h cube. Everything times forward square. Why not? So if we simplify again, of course, we know from our forward difference operator that this guy here can become y1 minus y naught. So I have this to be 2h y naught plus 2h into y1 minus y naught plus everything I'm seeing here should be 2h cube over 3, because I'm having 8 minus 6 basically. That's 8 over 3. And that will give me, so let's see, 2h cube over 3 times 1 over 2h square. 2h square can go with 2. H square, I have h over 3. So this is plus h over 3 into, now I'm saying for square y naught, that will be y2 minus 2y1 plus y naught from our forward difference operator. So let's simplify what we're asking. Let's simplify. We have this to be 2h y naught plus 2h y1 minus 2h y naught plus h over 3 y2 minus 2h over 3 y1 plus h over 3 y naught. Some things can go away. I can do away with 2h y naught minus 2h y naught. So everything here gives us, let's start with h2. I have h over 3 y2. For y1, I'm seeing 2h or 2 minus 2 over 3. That's 4 over 3. So this is plus 4 over 3 y1, then plus h over 3 y naught, which gives me h over 3 into y2 plus 4y1 plus y naught. So this is the Simpson 1-3 rule. This is how we derive the Simpson 1-3 rule. Question 3b says we should find the truncation error. The truncation error. The truncation error. Okay, we want to get the truncation error for the Simpson 1-3 rule. So our error is given as integral from 0 to 2h f of x dx minus the formula we got for the Simpson 1-3, which is h over 3 y naught plus 4y1 plus y2. Now the plan is to get the Taylor series expansion of f of x y naught y1 so that we can have this our error in Taylor series. So it becomes a bit long. Okay, so about the point x1, which is the same thing as h, we can say that our f of x should be equal to f of x1, or it's f of h, whichever it is you choose to write. But let's use it for x1 plus x minus h. Here also you can choose to write x minus x1, but because x1 is h, I can choose to go with my h like this. So x minus h f prime of x1 plus x minus h square over 2 factorial f prime prime x1. Can go ahead, say x minus h cube over 3 factorial f prime 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 x1, and so on and so on. In fact, x minus h to power 4 over 4 factorial fiv x1 then plus x minus h to power 5 over 5 factorial fvx1, and so on and so on. So let's keep it at this, and so on, so that we have more terms we are to consider. Now in our error, it says that we should get the integral from 0 to 2h. Now the reason why this formula is like this is because, you know, ideally this is what we did that we got this formula, right? So we are saying that if we should solve this problem normally the way we were taught in our calculus, we'll get a result. Which also will give us a different result. So the difference in the result is what we call the error. That's what I'm trying to analyze in this place. Okay, so we want to quickly get the integral from 0 to 2h of this function. So we have integral 0 to 2h f of x dx would be equal to integral 0 to 2h f of x1 plus x minus h f prime of x1 plus x minus h square over 2 factorial f prime prime x1 plus x minus h cube over 3 factorial f prime 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 x1 plus x minus h to power 4 over 4 factorial fiv x1 x minus h over 5 factorial to power 5, the fifth derivative at the point x1, and so on. All of this dx. So of course here the only variable we have here is x. So it makes every other variable we are seeing a constant. So this guy will be a constant. So I would have this to be x. This will be x f of x1, right? Or let me just say it is f1 so that I'll manage our space. So x f1 plus, if I would integrate this guy, I'm integrating only these two, right? So that would be x squared over 2 plus, minus hx times f1 prime plus the next thing will be here. I can how do I integrate this? So if we're using our by substitution, where say u is x minus h, our du will be dx, fine. So that's still u squared. So it is still to power 3 over 3. So I'll have this to be x minus h to power 3 over 6 factorial, or over 6 f1 prime. Then let's confirm again. If I make this guy u, so I have u equal to x minus h. Our du will be dx. So I'll be left with integral u square over 2, which is now u cube over 6. Now return back to what it is. That's x minus h. So it means that here also we could have just done x minus h all square over 2. It works. X minus h all square over 2. It will work. So we can proceed. So the next line for that one here, it will be x minus h to power 4 over, this is equal, that's 24 f1 prime plus x minus h to power 5 over 5 times 24, that's 120 over 120 f1 iv, then plus x minus h to power 6 over 720 fv1. Of course, all of this will be from 0 to 2h. So if we put 0 and 2h in each of these things, let's see what we'll get. For the first one, when x is 2h, I have 2h f1, quite alright. Here, when x is 2h, I get 0. When x is 0, I get 0. This is 0. The next line, when x is 2h, I have a plus. That's That's 2h, well, that's h over 6. That's h cubed over 6 minus, when x is 0, I'll have a minus h cubed over 6. So this is basically h cubed over 6 plus h cubed over 6. And I'll have it to be f1 prime prime. Okay, so for the next line, when x is 2h, I get h to the power 4 24. When x is 0, the same thing, that will be minus. So this is 0. This is 0. It means that this one should be 0. So here I should be having it to be plus h to the power 5 over 120 plus h to the power 5 over 120 FIV1. And then finally, we can say it is 2h f1 plus, this will be h cubed over 3 f1 prime prime plus h5 over 60 f1 IV. So everything we've just done here is to get this first part, integral from 0 to 2h of x dx. So now we should go and get what y0, y1 and y2 should be. Then from there we can bring all of them inside the same formula back and then we analyze. So if we be doing that, remember we are still using our Taylor series. We are still using Taylor series. So our y0, it can be written as f of x1 minus h. So we can say this is f1 minus h f1 prime plus h square over 2 factorial f1 prime prime minus h cube over 3 factorial f1 prime 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 plus h4 over 4 factorial f1 IV. Let me stop here, man. Let me stop here. Because the last thing I got here was IV. Of course, here there should be a continuation. It should continue. Because our integral here continues. We are only stopping at this point so that we have almost everything we need. Our y1, this one is simple. This is same thing as f of x1. So we are not going there. So this is our f1. Fine. And then our y2 is f of x1 plus h, and that will be f1 plus h f1 prime plus h square over 2 factorial f1 prime prime plus h cube over 3 factorial f1 prime 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 plus h4 over 4 factorial f1 IV, and so on and so on. So if we combine, remember our formula says that the error is equal to integral 0 to 2h f of x dx minus h over 3 y0 plus 4y1 plus y2. So putting everything we've gotten into this formula, we get our error to be equal to, this one here is already 2h f1 plus h cube over 3 f1 prime prime plus h5 over 60 f1 IV. Then I have a minus h over 3 into our y0 is f1 minus h f1 prime plus h square over 2 f1 prime prime minus h cube over 6 f1 prime 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 plus h4 over 24 f1 IV. Then it continues minus dot dot dot. So let me close this bracket for my y0 plus y1 is f1. Fine. Then I have my y2. Our y2, which will be plus, open a bracket, f1 plus h f1 prime plus h square over 2 f1 prime prime plus h cube over 6 f1 prime 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 plus h4 over 24 f1 IV, and so on and so on. So if we'll be simplifying our error that we've gotten here, let's simplify together. We'll have, So let's start with F1. Let's start with F1, just F1. F1 here, or in this bracket, in this whole thing, I'm saying F1. This is supposed to be 4y1. So this is supposed to be 4f1. So I'm saying F1 plus 4, that's 6, that's 5, plus 1, that's 6. So I have it to be 6f1 now over 3. That's 2. So this is minus 2h. Then I have it plus 2, that will be 0. So my f1s have given me 0. So 2h, f1, 4f1, and f1. That's 0. I want to move on to f1 prime. Here there is no f1 prime. Fine. Here there is f1 prime and it's carrying minus. And here I have plus. So that means that these two can go away also. For f1 prime, I have these two to be 0. Now, how about f1 prime prime? It is here, quite alright. It is here and it is here also. So, okay, let's see. For this bracket, it is 2 of the same thing. That will be 2h squared over 2. That's h squared. So, I have it to be h squared f1 prime prime times, in fact, let me bring it down. For f1 prime prime, here I have h cubed over 3. Then I have minus h over 3 into, I have here h squared over 2. Then I have here plus h squared over 2. So this is h squared. So I have this to be h squared over 3 minus h over 3 times h squared, which is h cubed over 3 minus h cubed over 3, and that is 0. So it means that everywhere I see f prime prime, that was 0. So I have this to be 0. This one is going away, and this one is going away. I'm left with prime prime prime. Down here I have minus, here I have plus, and that will be 0 also. So 0 and 0. I have one thing left, IV. So for f1 IV, let's see. What do we have? Here I have it to be h to the power 5 over 60. Quite alright. Here I have minus h over 3 into, I have that one to be h to the power 4 over 24 plus h to the power 4 over the same 24, which will give us h to the power 5 over 60 minus h over 3 into h to the power 4 over 12, which will give us h to the power 5 over 50 minus h to the power 5 over 36. And if we combine this, of course, we are not getting 0. So it means that our error, going by the first non-zero term we have, it is h to the power 5 over 50 minus h to the power 5 over 36 times f IV x1. FIV x1, because, or you say FIV prime. No, F1 IV. Anyhow. So if we combine this, what do we have? We have this to be the LCM here. The LCM here. No, let me combine with my calculator. So let me combine with my calculator. So I have 1 over 50 minus 1 over 36 to give me minus 7 over 900. So I have this to be minus 7 over 900 H5 FIV X1. Of course, our error is not, it should be negative. So we can take the absolute value. So I have this to be 7 over 900 H to the power 5 FIV X1. So this is the error. This is the error of the Simpson 1-3 rule. Oh, sorry. This is 60 here. So let me write my 60 back. Sorry, 60. So this is 60. So let's see again. If I combine, I'll have 1 over 60. That's a minor error. So that's minus 1 over 90. That's minus 1 over 90. And by the absolute value, I have it to be 1 over 90. So this is the error of the Simpson 1-3 rule. This is the error of the Simpson 1-3 rule. And of course, it is a fifth order accurate error. It is a fifth order accurate error. So that answers question 3b. Now question 3c. It says that using what we get in 3a, we should solve these two problems. So now that one will be very simple. So it says that we should evaluate integral minus 3 to 3 x to power 4 dx and integral minus 3. Okay, it's the same question. Well, I thought to evaluate just this one. Not this one. So if we were doing that using Simpson 1-3, recall the formula. The formula says that integral a to b f of x dx is equal to h over 3 y naught plus 4y1 plus y2 plus y2. Of course, here in our question, our x naught is minus 3, or a is x naught, which is minus 3, and then b is x2, which is 3. So therefore, our x1, which is supposed to be a plus b over 2, would then be minus 3 plus 3 over 2, which is 0. So we have everything we need. Integral minus 3 to 3 x to the power 4 dx would then be already our h. Our h is different in interval. So our h here is b minus a, right? Which is supposed to be what? 3 minus minus 3, and that is 6. So we have everything we need. Our h is 6 over 3 into y naught is f of x naught. So that's supposed to be f of minus 3 plus 4 f of 0, that is y1, then plus f of 3, which will give us 2 into f of minus 3. When I put minus 3 here, I'll get 81. So I have this to be 81 plus, when I put 0, I have 0. That one is gone. 3, 81, I have 81 also. This is giving me 2 times 2 times 81, which is 4 times 81, and that is so this is 4 32. So this is the answer, and that answers question 3c.